Welcome back to Signal and Control. Please see the following. Now we'll be starting with Part C, asymptotic approximation. So asymptotic approximation you will look at in Bode plot um, for the lower frequency and upper frequency and cutoff frequency and what happens to all the general cases. And we'll go through the examples. First, the log magnitude and phase frequency response graph versus function of a log omega, which are called Bode plot or Bode diagrams. There's a history and fun history of it, and it's good to read up on it. But let's concentrate on how to solve it. So for G of S, a system with a gain of K, we have poles, several poles up to number of K's. So 1, 2, and all the way. So all the zeros on the numerator and S to the M. So M will decide what type of system is. If it's 0, S to 0 is 1, and then that 0 tells it is a type 0 system. If you have a 1, then there's only S to 1, which is S, and then it is type 1 system, and etc. So we've been mainly dealing with S to the 2, which is type 2 system. And on your denominator, you have S equal these numbers, minus B1, minus B2, and etc. So those are the poles, and then up to n number of poles. So k number of zeros, n number of poles. The absolute value, now you substitute the S with the j omega, and the absolute value of it is your magnitude. How you do it? K comes as it is, and then you have to find absolute value of this, absolute value of this, absolute value of this, and you multiply it all. And S to the M, absolute value of it, divide by this, and all the way. So as S goes to j omega, so that's how you replace it. In logarithmic form, we always go with a 20 log 10 base magnitude of g of j omega. So first, do not forget, you do have to convert that k. So 20 log k, that is the first value. So that will set whether you're starting at 0 or if this was a 0, and then literally where your initial gain is. The next portion is you add all these, anything that's on numerator, you add them. Anything on denominator, including this S to the M term, absolute value of it, you subtract them. So let's start with the Bode plot, G of S, a transfer function, pure 0 at S equal minus A, assuming A is greater than 0, positive number. Then you would have the following. So you replace step 1, you replace S, wherever you see S, with a j omega. So g of S, g of j omega equal S plus A, j omega plus A. So you do a little bit of algebraic manipulation, so which I'm going to show you briefly. You take out A, and then this would be in j omega, and that would be in A, so it is literally same thing, but you are expressing with a gain 1 plus j, this is the real portion, and then this portion will be imaginary portion, omega over A. And then we will be looking at what happens to omega when it is infinity, or omega is equal to 0. So at a higher frequency, what happens? And what at the low frequency, what happens? As you can see, at low frequency, G of j omega is about A. Can you see that? G of j omega, how come it's close to A? So say omega is very small, then it's like you will have A times 1. You'll end up with only A. It's like a 0 plus A. So you're only left with A when omega is low. Omega is 2 by F. As F goes down, the frequency is low, omega is low. So the magnitude of something, so magnitude of this is 20 log m. Magnitude will be absolute value of it. Right? So instead of this highlighter, absolute value. And that happened to be A. So you replace m with A, 20 log A. Now let's look at what will happen to phase. So for it being what happens when it is at higher frequency, and you need to look at what happens to the magnitude and what happens to the phase. So let's look at G of omega, and it is you take this one with you, and then let's look at it. What happened to it when omega is high? So say omega is really high, then this term doesn't matter as much. So you will only see j omega, but that is still over a and times a. And then this one is not as significant as this term. So you end up with this. And then you will have, you can kind of cancel that, or even as it is, this will be the magnitude of it, and that is your m, and this is your angle. So for this one being m, a cancels out, you're only left with omega. How do we get the amplitude or the magnitude? We call that is absolute value of a g omega, and g omega, it being j omega, that's the same as 0 plus j omega. That 0 would be real term square, and then that omega will be omega square, and square root of it will give you square root of omega square. Well, it's officially plus minus omega, but for sine wave, it's pretty much the same. So omega, that's what you get. Now this is the fun part. You need to plot it. First, we plot magnitude. So before the cutoff frequency at A, it will be considered low frequency and 20 log A, and it's all flat right there. After the cutoff frequency, it will start to grow towards the infinity and higher frequency. So in a higher frequency, you'll see an asymptote that's increased by, let's look at 1 decade, and that's about 20 dB. So 1 decade per 20 dB per decade, because it's a 0. That's usually on your numerator. That's going upwards like this. So you draw a straight line up to that cutoff frequency or the break frequency at A, radian per second, and then you draw an asymptote 20 dB per decade. That would be your first step. So it's kind of gives slope of a y equal 20x. So this is the y, and this is the x-axis, the vertical axis and horizontal axis. and the slope is about 20 times the scale on the x-axis. For a phase plot for g of s equal s plus a case, what happens is phase degree, there it is at slope 45 degree per decade at frequency of your interest, that at A, the break frequency or cutoff frequency and many things you see, that will be exactly at 45 between 0 and plus 90. So when you're drawing your asymptote, we always had something happening at at the frequency A, radian per second, going 20 dB up that way. For the magnitude, instead of something interesting happening at that point, the flat starts 1 deca before frequency of interest and ends at 1 deca of your frequency of interest. So it starts, end, and in between where it crosses over is exactly the half at 45 degree. So there is something called normalized magnitude plot. So instead of it, look at this one, it's not frequency at 1 hertz or 10 hertz. The way how it is calculated, it's a frequency divided by a rad per second. So it's normalized in a way. So it's omega over a. So let's look at normalized magnitude plot. What do you mean by? It's a magnitude plot still in scale 20 log, but this is m, the absolute value of your system, over a, which is your y-axis. X-axis, it is your frequency over a. So all of a sudden, when you see 1, it's not 1 hertz. It is a frequency, omega, that you're sweeping from 0 to megahertz and kilohertz, are like a huge number of higher frequency, low frequency to higher frequency, to pi f, when you're kind of sweeping from very, very small all the way to the big. But you're dividing that omega over a. A is a fixed, that is part of your system, and omega is what happens to the system output when you're sweeping 0 to infinity. So something interesting happened when that exact frequency in radian per second to pi f, it's in rad per second, and a, they are the same, omega equal a. That becomes 1, and that's what this is. So the nice thing about this normalized magnitude plot is you can compare what happens to the system in different frequency, and you can normalize it all to 1. So it depends on how these graph comes out, and you can kind of tell and compare systems with different frequencies. So in a nutshell, before that one, it's a flat. After that, you have an asymptote of 20 dB per decade. So 20 minus 0 and 10, 1. So that's 10 times. So this slope is 20 dB per decade. I'm going to conclude it with a normalized phase plot. If we did a magnitude plot, we need to do a phase plot. So the same place, the frequency omega, or 2 pi f, rad per second, over the place that we're interested at, you're interested in something happening at A, you will see 45 degree shift at that place. So this blue line, I'm going to try it in a blue, thicker but smaller lid. So this blue line that you see, it goes right through 45 degree, but that's happening at 1. So you need to kind of start at 1 point, like divided by 10, 1 deca before and 1 deca after. Then your asymptote will look like this. Then your real graph, when you're drawing it, you do have to calculate it where it's crossing. It's a nice smooth curve looking like, or somewhat going, and then there's a cross point, and it will be like a nice small S-like wave, not like this, but more like this. It is a little bit harder to draw, but if you get a interesting point and then calculate it exact value, somewhere around here, then it will be easier to find and then draw your graph according to it. So this concludes the Bode plot, both magnitude and phase, regular and normalized. G of S when the system G of S is S plus A. I'll show you in the next few videos for cases 1 over S plus A and other cases, and eventually we should be able to plot any type of a system with the several poles and zeros and gains and for different systems.